Hello, Assalamualaikum. Welcome back for our today's lecture on mixed strategy. So it will be a quite interesting and simple strategy. We are still under Nash equilibrium. Uh, okay. And before we start our class, so they have three announcements. The first announcement today from 4 to 5 o'clock, I will do a forum or live chat using WebEx. So regarding pure and mix on classical and Nash equilibrium, so you can ask me anything that you if you have still have problems regarding the method or how to differentiate when we need to use prisoner dilemma or when we need to look on what is the difference between decision theory and game theory. Okay, you can ask me questions from 4 to 5. Then do remember that's the first announcement. Second announcement, this week I will distribute your assignment one I will distribute on Thursday. Okay, according to our teaching plan. And the last one for this week on Thursday, we will have online quiz. Okay, we will have online quiz where I'll give you question and you all need to open your camera and need to answer and send back to me. Okay, in online I plan to do it on Thursday 10 o'clock. Okay, Thursday 10 o'clock we'll have online quiz around 30 minutes and we will continue another 30 minutes with some exercise. Then on night we will do discussion on mixed strategy using Gambit R software. I still have I still have in mind between Gambit or R. Definitely I will go to Gambit for a while and I will also show on R. So I hope all of you already download R. If don't download yet, if didn't download yet, no worries. I will give you the link. It's very easy and it's also quite uh, very small in term of size. Okay, so that's so let's continue. Mixed strategy. Instead of playing poorly up or down, player A can select a probability distribution pi u, okay, pi u or 1 minus pi u, meaning that one probability pi u, player A will play up, and with probability 1 minus pi u will play down. Player A are randomizing. Randomizing here is called mixing between both strategy. Okay, because in do remember usually as I previously mentioned, this is the beauty of Nash equilibrium, because Nash equilibrium already told us that if you don't find any single pure strategy in a pure strategy, any equilibrium in pure strategy, you always can find at least one in mixed strategy. So this is how they're randomizing the strategy. Okay, the probability distribution pi u and 1 minus pi u is a mixed strategy for a player A. Okay, similarly same goes for the player B, where it selects probability distribution pi L and 1 minus pi L, meaning that pi L player will play left or 1 minus pi L will play right. And also player B also mixing over the pure strategy, and this is why I'm surprising why most of you can answer. I don't know from where you get the answer. You can answer the question of question number 2 and question number 3 especially. Okay, so in here we will learn how we get that solutions. Okay, so let's look on the next part. Okay, let's look on this example. So you have player A that playing up. Okay, let me open the pointer. Okay, playing up or down, while player B is playing left or right, and this is the payoff given. So you know that if player B plays left, her expected payoff, if player B is player left, again, if player B plays left, so the her expected payoff will be, because their player B, we are looking at the player B, that's why we take 2 pi u, because it depends on the expected payoff of player A, 2 pi u. plus 5, 1 minus pi u. Okay, but the same thing goes when player B is playing right. So we know that 4 pi u plus 2, 1 minus pi u. Okay, so next what we do? So if 2 pi u plus 5, 1 minus pi u is more than 4 pi u plus 2, 1 minus pi u, then we definitely will play left. But there are no Nash equilibria, correct or not? Because we already know there are no Nash equilibrium in which we play left. Because we know that B always will choose if playing left, always we choose playing right, because right is giving us more. If playing up, for playing up, we're definitely giving more payoff compare plays only left. So B will play only right, but if now if you can look here, okay, previously if you look here is more. If this one, the left hand side is more than right hand side, then definitely B only play left. But here we doesn't have any equilibrium in the left. So next, we're doing the same thing. If it's less than, it means this left will be higher than the right. Okay, but there are also no Nash equilibria where which B plays right. So finally, what we'll do, so for there to exist a Nash equilibrium, B must be indifferent between playing left or right. That's why we make it this equal sign. Now you understand why I put equal signs? Okay, because we don't know, we don't know is it they're playing left or right. That's why I put equal sign. And finally from here you can find the probability of pi u is 3 over 5. Definitely if the here is 3 over 5, definitely this one will be 2 over 5. The same method we're using for player B. Okay, look, if player A plays up, okay, and up, his expected payoff will be 1 because they took this 1 times PL plus 0. 1 minus pi L equals to pi L. Do the same thing for the if playing down, the expected payoff with playing down, and same pi L more than 3, 1 minus pi L, then A will play only up, but in this case no Nash equilibrium in up. So we look the next possible strategy. If A we play only down, but there also no Nash equilibrium which A play down, so finally we make it equal. And from here we can know that pi L is equals to 3 over 4. And we already know if here is 3 over 4 and here is 1 over 4, so we will have, so the game only Nash equilibrium has a playing mix strategy, okay, which is 3 over 5 or 2 over 5. It means randomizing on both strategy, and has B playing the mixed strategy 3 over 4 and 1 over 4. If we look here, this is the first step to solve the game. But if we want to find the expected value of A and expected value of B using this mixed strategy, Nash equilibrium will be calculated using next. Look at the next video. Thank you. Okay, next let's continue now how to calculate the A expected payoff and B expected payoff. So pointer option. So if you look here, the payoff will be 1 and 2 with probability. So when you already have the payoff here, you're just using the probability that you get just now. It means that 3 over 5, so this one, times with 3 over 4. So this is the same procedure how I get the question number 1C and 1D answer, okay, for the last week tutorial. So if 3 over 5 times 3 over 4, you will get 9 over 20. Next, you need to do the same thing for the rest of the matrix. So here you get 3 over 2, 6 over 2, 2 over 2. This is the first step. Second, what you should do is you can calculate now the A's expected Nash equilibrium payoff. Okay, if this is the example. Okay, so what you should do if you want to find the A is always for the first player, correct or not? So that's why they took this 1 times the total value of that probability. It means 3 over 5 times 3 over 4. So 9 over 2 plus, take again the first value 3 over 20 times 0 plus 0 6 over 20 and finally plus 3 times 3 over 20. Basically we get 3 over 4. You need to do for the same thing for the expected Nash equilibrium for B, so you will get 16 over 5. So here, if we want to look the final game of A expected Nash equilibrium and B expected Nash equilibrium is 3 over 4 and 6 over 5 with the probability mixing together of player A 3 over 5 and 2 over 5, and for player B is 3 over 4 and 1 over 4. Okay, this is the way to solve the question 1C and 1D. Okay, so how many Nash equilibria? A game with a finite number of layers, each with finite number of pure strategy, has at least one Nash equilibrium. So it means that this is the beauty of Nash equilibrium compared to classical theory of game theory. So if the game has no pure strategy Nash equilibrium, then it must have at least one mixed strategy Nash equilibrium. So do remember, we have three ways to solve any matrices. First, if you have only 2 by 2, we can use Nash equilibria, if you still remember. Second, if you still remember, we already learned on dominate strategy. What is means strictly dominated, what means of weakly dominated. Okay, and the third one, so what the purpose you're doing weakly dominated or strictly dominated to reduce the size of matrix, hopes to go back to 2 by 2 so that we can easily solve that issue. Okay, but it's not necessarily only 2 by 2. Okay, sometimes it can be very complex matrices. Okay, and finally we can use on saddle point. Okay, on saddle point, but here I will talk more on Nash equilibrium and also on dominate strategy. So after this we will look on the dominate strategy. Okay, so elimination of dominant strategy as the alternative route of Nash equilibrium in order to reduce the number of matrix, the size of matrix. So example, let's say you have U, M, and D, upper, middle, and down, and left, middle, and right. So if you look here, this is the example of the value, and can you determine whichever sum of the dominant strategy? Okay, let's look on the M, 5 1 8 4 6 9. Okay, and you can play between player 2 or player 1, up to you. Okay, so if you take this one, okay, okay, let's continue in the next video. I'm sorry because now the loom is only give maximum 5 minutes. This is why I have to do a lot of videos. Okay, thank you. Okay, let's look on the last method how we can use to eliminate for dominated strategy. And look here, in here we only focus on the strictly dominated. That's how I'll show in the previous lecture, and also in the Gambit software we only look on the strictly dominated. Okay, so let's say this is the questions for 3 5 1 6 2 2 1 8 4 3 6 3 0 9 6 and 2 8. And let's look now from player 2. Okay, let's say we start with player 2. Okay, for this question I say let's start from player 2, and we look here. 3 is more than 1, 2 is more than 4, 0 sorry 3 is more than 1, 1 is lesser than 4, 3 is lesser than 6. So this one we cannot use. So let's compare this one. 2 is more than 1, 6 is more than 4, 8 is more than 6. So it means that we already know R will dominate M, correct or not? So that's why we will eliminate M, because we already know R will always dominate M, and definitely player 2 definitely will never play M. So next, so when we already start to eliminate the particular column, when it's already strictly dominated, we will eliminate the particular column and throw away. Then we will left with 2 columns here, and we still have three rows. So next, let's look on the row. We have 4 2 1, sorry, 4 2 3. 4 is lesser than 6, 2 is lesser than 2 is lesser than 3, and 3 is lesser than 2. Okay, 3 is lesser than 2. So from here we can know that, sorry, 4 is more than 2 and more than 3. 6 is more than 3 and more than 2. And if you look here, 2 is lesser than 3 and 3 is more than 2. If you look here, we have weakly dominated. That's why we know that if you always we dominate M and D together, because 4 is more than 2 and 3, 6 is more than 3 and 2. So that's why we only left with left right with two columns and one row. And finally, when we look back on the second column, and in the second column, 3 is more than 2, definitely L is always dominate for R for player 2. So finally we have always for this game they always will play the Nash equivalent will be U and L, 4 and 3. Okay, now I hope you understand how we can use elimination dominate strategy, either using strictly dominated or weakly dominated, in order to solve the issue. So here UL is the only solution of the game. And do remember, in the real life a dominant strategy may not exist. Okay, this is an example. If it exists, we can have an alternative solution, but do remember a dominant strategy may not exist in the real world, because let's look on this fact. Example, in the telephones industry or technology industry, they always will never have a dominant price or dominant advertisement or the factors, because most of the industry will do the same thing. And here there will be more tricky or conflict situation where we do not have a dominant strategy. That's why we need to understand the historical pattern in the game theory. In the game theory, the most important thing of the data is the historical pattern, what they already done, what they already going to do, and how they will going to achieve it. Okay, that's all for today's lecture. So it is very easy, right? So next, what I will do, I will discuss the question number 3 discussion, question number 3 tutorial in the coming video or lecture, since we are going to discuss on it, to discuss on it. And you can also ask me in afterward when we are doing a live chat, because on coming Wednesday the first class will do the quiz, and in the night we're doing on the software. Okay, thank you very much.